So before we dive too far into the kind of details of seismic certification, I just want to kind of give a brief overview of really what we look at from seismic requirements and non-structural systems. Uh, Probably anyone that's on this phone call that's a structural engineer can attest to the fact that non-structural components are something we learn little to nothing about during engineering training, whether it's from a kind of structural engineering curriculum in college and really on a day-to-day basis. And so it's sort of this gray area, this nebulous item that we sort of deal with as structural engineers, but don't necessarily fully get enveloped in. Normally, a lot of the non-structural aspects outside of certain specific industries fall kind of on a delegated design responsibility where we sort of push off the requirements to kind of design build installation contractors or off to the manufacturers. So it's something realistically as structural engineers we don't necessarily dive into with a great amount of attention during our careers. But sort of I always like to take structural engineering and really think of it as a learn as we go industry. And so we learn a lot from earthquakes. We see a lot of what happens, what we thought was going to happen, and basically our code adapts based on observations we see, whether during earthquakes or during um, a research program in which we kind of see how systems actually behave. And so in the past, we saw a lot of non-structural systems that were damaged over the years, and our code sort of adapted, and we created more requirements for consideration within the IBC, within the ASCE 7 document for what focused primarily on position retention of components. As time went on, we still adapt this code on a year-to-year basis. I kind of put these photos up here because these are a variety of failures from relatively recent earthquakes, as well as some relatively new structures that should have been designed properly by code for non-structural systems, but still had rather substantial failures, whether it be mechanical and electrical systems, architectural components, and building contents. So really the big question always comes down to, obviously we don't want to have an air conditioning unit fall on our heads, but, beyond that, what's the reasoning for a need to have more attention paid to non-structural systems? And this is sort of just a very basic broad graph, but, we talk about and we have a great amount of pride as structural engineers in the buildings we design. But at the end of the day, the actual building, the structure itself, accounts for a relatively small portion of the actual investment an owner makes. And actually, the non-structural systems and the contents in the building, really, that's the investment an owner is making. That's where the majority of their money is going when they build a new system. And so, from an economic standpoint, there's a huge reason that we need to pay attention to non-structural systems, aside just from the safety aspects of it. We also see that there's a substantial potential or a potential substantial impact of failure of non-structural systems in certain aspects. This is obviously just a photo of the Fukushima Daiichi reactor. Now, it didn't fail because of the earthquake. It failed because of the tsunami that ensued, but it at least points to the potential impact that certain failures can have on a community and on a region in the event of a failure of a non-structural system. In this case, an emergency generator that couldn't function after an earthquake to provide cooling water. So non-structural systems play a huge role in performance-based engineering. When we talk about sort of the range of what we consider from a design, performance mentality, we look at sort of the idea of having a building that after an earthquake is fully operational and working, all the way down to a building that is on the verge of collapse. When we take a normal structure, an everyday kind of office building type structure, we're focused on a risk category 2 system where we're trying to preserve life and make sure the system is not basically falling apart and posing a major risk to life and safety of occupants and those surrounding the building. We get all the way up to the operational mentality, and we're basically saying that, hey, I don't care just about having my building stand up, but I want to make sure my building stands up and after the earthquake functions. It has power, it has whatever essential systems that I need for this building to continue working, and I have those intact.